Hello, my name is Kathryn Chapman, and today my colleague Marcel Schwarz and I will be presenting our paper titled Multilingual Medical Entity Recognition and Cross-Lingual Zero-Shot Linking with Facebook AI Similarity Search, which details our submission for the LivingNER Shared Task 2022. We'll begin the presentation by providing some background information, which is useful for the next section where we describe our model architecture. Then we will discuss the experiments we conducted, the results, and finally conclude with a discussion. We will first discuss something called Self-Alignment Pre-Training BERT, or also SAP-BERT. SAP-BERT, which is described in more detail in the paper Self-Alignment Pre-Training for Biomedical Entity Representations, is essentially just an encoder that takes an existing BERT-based encoder and further pre-trains it on synonyms that are extracted from UMLS. What that means essentially is that, for example, the vector for cryptogenic embolism stroke is similar to the vector for acute ischemic stroke, as these two synonyms are belonging to the same medical concept of ischemic stroke. To better illustrate how SAP-BERT works, we have provided the following visualization. Each point here represents a vector of an encoded textual description of a medical concept in UMLS plus all of its synonyms. We've performed dimensionality reduction and projected these encoded medical synonyms into this vector space. The synonyms are color-coded by the preferred term which they are a synonym of. So for example, in the middle, we see a lot of light gray dots. These are all synonyms of myocardial infarction, also known as heart attack or cardiac attack, and so on and so forth. So each of these dots is representing a different synonym. So as we can see, what self-alignment pre-training does is it takes those clusters of synonyms which correspond to a given medical concept and it makes them closer together so that we don't have overlapping clusters. We have smaller, tighter clusters. We will now discuss Facebook AI Similarity Search, which is also known as FAIS. FAIS is an open source library designed by Facebook to search billions of data points of content to recommend similar content for a user based on their interests. But first, it's important to describe exactly what similarity search is. Similarity search is when we have an index of vectors, as we see here on the right, and a query vector, the goal being to find in that index of vectors the most similar vector to the query vector. If our index is extremely large, searching this index can take a lot of time, as we're comparing every query vector to every indexed vector, and this is not very suitable for production software. So this is where FAIS comes in. It allows us to search very large indexes efficiently. We will now discuss our model architecture. A general overview of our model is illustrated in this graphic, which we will now break down step by step. We first perform named entity recognition with a SAP-BERT XLMR encoder and a conditional random field classifier. Entities which the NER step identifies as human are then linked to the NCBI code for human. All other entities are then re-encoded without their surrounding context with a new off-the-shelf SAP-BERT XLMR encoder. The re-encoded entity is then passed as a query vector to a FAIS index of all encoded NCBI code descriptions and synonyms. If there is no vector in that index meeting the criteria of a predefined similarity threshold, we break the entity down into smaller fragments, re-encode those fragments with SAP-BERT XLMR, and search the index again with those fragments as our query vectors. If at any point the distance threshold criteria is met, we link the entity to that corresponding NCBI code.
We use two different FAIS indexes in our experiments. The first smaller index only contains the annotated text spans from the training data as synonyms for the labeled concepts. If a synonym was associated with multiple concepts, we only assigned it to the concept that it was most frequently associated with. This means this index has some task-specific knowledge, where it knows for ambiguous text spans what the preferred concept is by the annotators. It can also deal with the complex codes that appeared in the training data. Overall, this index has about 850 concepts and 2,400 synonyms. The second index is much larger. It contains all the English and Spanish synonyms from the provided NCBI dataset. On top of that, we used the Unified Medical Language System, UMLS, which contains many different medical ontologies. If an NCBI concept also appeared in another ontology, we added the Spanish synonyms to the index. Overall, this index contains 1.76 million concepts and 2.46 million synonyms. From our experiments on the validation data, we could see that the large index was significantly outperformed by the small index. Even a combined index still performed worse than only the small index. We can see why that happens with these two examples. In the first examples, we tried to link the text span enterovirus, which is typically annotated with the concept you can see here, which stands for human enterovirus. While our large index simply links this to the general concept of enterovirus, our smaller index doesn't even contain that concept, but it knows that this synonym is commonly linked to the concept of human enterovirus because the corpus is generally about humans and human viruses. In our second example, we have the text span virus influenza A, which is typically annotated as concept 11320, the influenza A virus. And we can see that our small index only contains that concept for this synonym. However, the large index contains another concept with the same synonym. And if we have cases like this with overlapping synonyms, the large index would not know which synonym was preferred. To combine the strength of both indexes, we use a two-index approach, where first of all we search a text span within the small index, and if we can find a synonym below a certain distance threshold, we directly link the text span to the corresponding concept. If we cannot find a close synonym, then we assume that the text span represents an unseen concept which has not appeared in the training data, and we search it within the large index. We can see that this specifically improves our recall as we're overall able to identify more concepts. However, the F1 score is not very good at capturing a model's ability to identify rare codes. In this graphic, we can see the distribution of codes within the training data. There are only very few codes that make up the majority of linked entities, and then there's this very long lagging tail of entities that appear very rarely, most of them only once. So if we measure how many unique codes were identified at least once, we can see a big increase with the combined index. The small index identifies about 63% of codes, while the combined index identifies over 75% of unique codes. And here we can see our updated model architecture for the two-index approach. And finally, our results on the test set. For subtask 1, we achieved an F1 score of 88.7. And for subtask 2, our model achieved an F1 score of 87.4.
We will now provide a closing discussion on our model, in particular the strengths. For starters, our model is production suitable as we have developed for internal use at IGES a model based on this described architecture. It's multilingual and can perform on any of the languages which XLMR Roberta is trained on, but in particular we use this for English and German. We were able to annotate all 34 million abstracts on PubMed at about 0.2 seconds per abstract in under a month. The use of FEIS allows for scalability in that we can have very large indexes with millions of synonyms, such as those in UMLS. Additionally, the use of zero-shot entity linking means that our model is robust against the label imbalance problem. Essentially, labels or medical codes that don't occur very often in a data set can still very easily be retrieved based on their textual descriptions. Additionally, our model is multilingual and flexible to any entity recognition and ontology linking task.